Hi, my name is Christina Wetzel, and this is my lab report for Lab 2, Charged Tapes Continued. This lab report has three main parts. The first is the introduction to the lab. Here, I'll outline the purpose, principles, and results of the lab, as well as the data I previously gathered during the Lab 1 Charged Tapes experiment. The second is the data and calculations for this lab. In this section, I will explain and show the code used to calculate the charge in the experiment, as well as the model generated by the code that represents the experimental system. The final part is the conclusion. Here I'll examine the reasonableness of my results and assumptions, as well as ask some important questions about the lab as a whole. The overall purpose of this experiment was to again find the charge on a charged piece of floating tape, but to do so using a computational model that modeled the tapes as evenly charged lines instead of point charges. A general difference between the two models is shown here, with the green and orange being the last lab's models and the blue and red being the models used for this lab. The principles used in this lab can be seen here as well. Coulomb's law is used in this lab to calculate the electric field from one point charge at another location, specifically that of points on the bottom tape on points of the top tape. Newton's second law is used to show that the electric force on the top tape should equal the gravitational force on the top tape, as the system is not accelerating. The superposition principle in this lab says that the net electric force should equal the sum of all the electric forces of each piece of the tape put together. The results from both Lab 1 and this lab can be seen here, with a new calculated charge value of negative 6.90156 times 10 to the negative 9th coulombs for the floating tape. To recap, the setup for the experiment is shown here, with two charged tapes that were created by pulling pieces of tape apart and saving the top charged pieces to float them above one another. The data gathered from the experiment is recorded here. The computational model involved several key steps that I will explain here. The first thing I did was to find some key constants and values from the experimental data for later use. Q was originally my value from Lab 1, but was later adjusted until the correct field was obtained, giving me the calculated Q value, or final result for this experiment. The code version of Coulomb's law is also present here as a function, in order to be used in future calculations. This function is the tape splitting function and creates our line charges made of tiny charged pieces. The sum of all of the charges equals the total charge Q, and the sum of all the tiny masses equals the total mass M. It is used at the bottom to create the top and bottom tapes 1.1 centimeters apart. I split each tape into 18 pieces for this experiment, but theoretically the more pieces the tape is split into, the more accurate the result. For the final part of my code, I create loops that go through each segment of the top tape and calculate the net electric force due to all the pieces of the bottom tape, via the electric field function and the fact that electric force is equal to charge times electric field for these modeled point charges. The superposition principle is important here, as the net force for each top piece is calculated as the sum of all of the bottom forces combined, and the net overall force is the sum of all of the results for the top pieces. These results are modeled at the bottom with the creation of scaled arrows, as you will see on the next slide. Here is the model generated by my code, with the red top tape and the blue bottom tape modeled as charged lines, the green arrows showing the electric field at each piece of the top tape by the bottom tape, the white arrow representing the net electric force, and the yellow arrow representing gravitational force. The white arrow was initially too small with my charge from Lab 1, so it was adjusted until the forces were equal, as Newton's second law implies for a floating object. This calculation relies on the assumption that each piece of tape had about the same amount of charge distributed evenly along the tape. The gravitational force and electric force can also be seen at the bottom. Overall in this lab, we no longer neglect the fact that the tapes are charged throughout and cannot be modeled as point charges. The newly calculated charge is larger than the one calculated in Lab 1 using the point charge model. This makes sense as the new model takes multiple force contributions into account instead of one average value in position. This should logically find a larger number. The value found in this lab, because of its more realistic model, is likely closer to the real value as well, and takes the separation of both tape charges into account, as well as the distance apart and mass. Some overall assumptions used include conservation of charge, or that the sum of the pieces of charge tape must equal the total charge Q, that the tapes are treated as uniformly charged rods, that no net external forces act on the tape in the x direction, and that each tape has the same net charge. That's it for Lab 2. Thanks for watching.